Excitation in a neuron results from the change from resting potential to the action potential in the axon body. During resting membrane potential, the inside of the neuron is negative, while the surrounding outside of the neuron is positive. This is the homeostasis of the neuron. The resting potential has a given voltage at all times. This can be seen on the voltage versus time graph. In order to achieve a signal down the neuron, the process must start with some sort of excitation. This is from an outside stimulus. This changes the voltage. In order to actually get a signal to travel down the axon body, this must reach the threshold potential. This means that you can have excitations from outside stimuli that don't actually quite reach the threshold so that they don't send a stimuli down the axon body. Once the voltage change is large enough so that it changes down the axon body, action potential is achieved. When axon potential is achieved, voltage-gated ions are opened up. These are sodium voltage-gated ions. This allows sodium to flow into the cell. This changes the inside of the cell from negative to a more neutral, positive-ish charge because of the positivity of the sodium atoms. The force driving this is equilibrium. This step is called depolarization because the inside of the axon body is becoming depolarized. This increases the voltage exponentially. Once it, however, reaches a certain voltage, the sodium ions will shut. However, these sodium ions are already in the cell, some of them are, and they will begin to diffuse down the cell, causing a depolarization wave in the cell. This changes the voltage for different channels down the cell, causing more sodium to flow through. There are, however, also potassium ion channels. These potassium ion channels pump potassium ions out of the cell in order to maintain the polarization within the neuron body. So, in order to do this, the positives must go out of the cell to try and maintain that homeostasis. This causes the voltage to drop way down. However, it doesn't just stop at the threshold or the resting potential, it actually undershoots the resting potential quite significantly. This is because equilibrium is driving this. Once it reaches this voltage, the potassium ions will shut. This is all called hyperonization and will flow down the cell as well. The resulting wave that flows down this cell looks something like this. Because of this undershoot, we get a refractory period in which sodium ion and potassium ion pumps sodium and ions and potassium ions into and back out of the cell in order to maintain the proper homeostasis with a larger concentration of sodium outside of the cell and a larger concentration of potassium inside of the cell, which got reversed during action potential. Because of this undershooting and returning to the resting potential, this is why signals cannot flip back around. They can only go in one direction. This is because these transmitters are turned off, partly because the voltage is below the resting potential, and we would have to get all the way back up for the threshold potential for the sodium ion, and then secondly, because we need to return to that homeostasis so that there are more sodium ions to pump into the cell before we can transmit another signal.